All right, we take a look at another example. So it says a journal reported that the mean height of begonias grown while being treated with a particular nutrient is 30 centimeters. To check whether this is still accurate, heights are measured for a random sample of 20 begonias grown while being treated with the nutrient. The sample mean and sample standard deviation of those measurements are 31 centimeters and 10 centimeters respectively. Assume that the heights of treated begonias are approximately normally distributed. Based on the sample, can it be concluded that the population mean height of treated begonias differs from that reported in the journal? And we'll use a 0.05 level of significance. All right, so it doesn't say test the claim, but it says, can it be concluded? So that's equivalent to saying test the claim that the population mean mu of these treated begonias differs from that reported in the journal. The journal reported that the mean was 30 centimeters. So let's start with our hypotheses. So we have our null and our alternative. I focus here on the claim being made, and that's that the mean height differs. So it's not equal to the number stated in the journal, and that was 30 centimeters. All right, the null hypothesis would be that the mean is 30 centimeters. So in hypothesis testing, we start with the assumption the null is true. So we start with the assumption the mean is 30 for the population, and then we're going to go gather some data and see where our sample mean falls. All right, so they did that. They went out and got some data. So they took a look at 20 begonias, and the sample mean and sample standard deviation are provided, 31 centimeters. And again, sample standard deviation is S. That's the important part here. That's sample standard deviation. So as soon as I wrote that, I know that I'll be using a t-test, not a z-test. We don't know sigma. And the alpha they'd like us to use, significance level alpha, is 0.05. I like to write that as a percent as well. So 5% significance level. All right, before I do the test value, I just want to focus on traditional methods set up first. So anytime it's a not equal to, it is a two-tailed test. So to find the critical value, we can use the table, or you can use inverse T if you have it. So I'm just going to mention here that on your T table, you look at the column. So it's a two-tailed test. So your table has a column that says two-tail alpha. Two-tail alpha. So if alpha is 0.05, you can go to the column that says two-tail alpha, and then go to your degrees of freedom, n minus 1. In this case, 20 minus 1 is 19 degrees of freedom. And we need to remember that for a two-tailed test, there are going to be two critical values, one on the left and one on the right. The table will not tell you that. It will just give you a positive value, and we'll know that it has to be a plus minus. All right, if you have the inverse T on your calculator, you could use that as well. So alpha over 2, in this case, because alpha will be split in half, half on each side. So if we take 0.05 and divide by 2, alpha over 2 is 0.025. So before I go to the calculator, on the table, the two-tail alpha you'll be looking at two tails. That looks weird. Two-tail alpha, you'd be looking at alpha equals 0.05. But alpha over 2, then, that number would be the area in one tail. So just for a moment, I'm going to go back to a previous page where I had a cutout of the table. So let me just focus on alpha in one tail. So back on a previous example, I'm just going to get rid of my numbers here. So you see how there's a one tail alpha, 0.05. That's not the one we want because we're doing a two-tail test. So I don't have a whole table over here. You'd have to come over to another column. You'd be looking for two-tail alpha. So it's important that you're looking at, for a one-tail test, all your alpha there. For two-tail tests, you're looking in that row, right? Or you can use your calculator. So let me go ahead, so I don't have to flip over to a table right now. Let's find our critical value, and I should say plural here, critical values. So t equals, and it's going to be plus minus, but you can find at least one of them by doing inverse t, your alpha over 2, degrees of freedom. All right. So inverse t, 0.025, 19. So that's giving us the -1, but again, it's going to be plus minus, and that will be negative 2.093. So plus or minus 2.093. So on the table, you'll just see 2.093, and you have to remember to put the plus minus in for the two-tail test. All right, so let's take a look at the graph then. So 2.093, basically at 2 there. So we have a critical value there, critical value there. So there's our negative and our positive critical values. And we had to do that because in a two-tail test, half of your alpha is on each side. So half of alpha on each side, left tail, right tail. And that creates two critical regions, those z-scores to the far left and those z-scores to the far right. And I just said z, very sorry, t. The t values to the far right, the t values to the far left. So process is the same, just having to have this conversation about going to your table or using your calculator to find critical values. The rest of it, the calculator can take care of for us when you run a t-test. So the t-test does not do the traditional method. So it does not provide that for you, but it will give you everything else. So let's go to our t-test. So t-test. And our mu naught was 30 centimeters. Our x bar came out to be 31 centimeters. S was 10 centimeters. Sample size of 20. We're doing a two-tail test, so we want to make sure to pick not equal to. And then all right. So my test value, my t value is 0.447. And we're just rounding t's to 3 decimal places because that's what the table provides. So just matching that rounding. And then the traditional method says graph that. And that's telling us on the graph where our x bar of 31 is. So 0.447 test value tells us that 31 is there on the X bar graph. So we're definitely in this unshaded non-critical region. So that number falling in the unshaded critical region. So my test value falls in non-critical region, which means that our decision, I'm just writing it once down here because both methods will give the same decision. So when you're not critical, do not reject the null. So we do not reject H naught. So 31 is not different enough from 30 to convince me that 30 is incorrect. All right, so p-value method. So for p-value, here's our 30. And the only thing we graph is our test value to start. So that told me 31 is there. So the only thing you have to remember with graphing p-values is that this area to the right of it is only half your p-value. So in a two-tailed test, just like alpha is split in half on either side, the p-value area is split in half. So in order to graph it, what we do is look for the partner of this number on the opposite side. So this is not a new test value, it's just the opposite sign partner of the test value. So there's no name for this number. I just call it partner just to call it something, just my own made up word there really. But in order to graph the rest of it, I'm sorry, that does not look perfectly symmetric, but the rest of that area that is your p-value, so the other half of your p-value is on that side. So when you graph a two-tailed test, you'll see shading on both sides representing your p-value in total. So on my calculator, I am going to just go ahead and do my draw option. So if your calculator is set up and it can draw for you, that's the picture of the p-value method, and you see that shading on both sides. All right, so hopefully it's clear from these two pictures that these two together, the p-value areas, are definitely bigger than those two together, the alpha areas. So I can see that my p-value area is definitely bigger than my alpha area. And I can now record the numeric value. So that is a little small for my eyeballs, 0.6598. And I am just going to quadruple check here and do calculate because the screen is bigger, 0.6598. So 0.6598. That's a really big p-value, 65.98%. So 65.98% is definitely bigger than my alpha, which was 5%. And the rhyme is, if your p-value is low, let the null go. But my p-value is not lower than alpha, it's bigger. So we do not let the null go. So as always, these kind of are puzzles that have to fit together. If your test value isn't in the critical region in the traditional method, that guarantees that you've got a big p-value. So a p-value area bigger than alpha. And those two things lead to do not reject the null. And then we complete our sentence. So based on a sample of, that was 20 begonias. So based on a sample of 20 begonias. And at a 5% significance level, we don't reject the null, then there's not enough evidence to support the claim. And this was the mean height of begonias differs from 30 centimeters. All right. So there's an example for you of a two-tailed test using the t-distribution.